Okay. Yep, so thank you to the organizers for organizing this workshop. It's been great over the last few weeks, seeing so many interesting presentations, and actually a lot of the work I will discuss today has actually been mentioned in parts in some of the other presentations, so that's been quite useful at setting up a lot of the background material, which hopefully should lead in a bit more naturally to some of the stuff here. So it's quite a broad sweep of a title, and it's possibly not the most informative in the world, but my aim in this session is to consider various developments that have been made recently, particularly in the pseudo-marginal MCMC literature, in kind of reconsidering how we perform inference in systems where we're kind of necessitated to use pseudo-marginal methods, so where we have some sort of intractability in the density that we're evaluating, and considering if we can leverage structure in that estimator in terms of some set of auxiliary variables to perform MCMC in an augmented space as opposed to just the original target variables we're looking at. So most of the work of my own that I will be talking about was completed during my PhD at the School of Informatics in Edinburgh. And this was work both with my supervisor, Amar Storkey, and also with Ian Murray. So I'll try to acknowledge specifically the projects we were involved in later on in the talk, but yeah, they were a key part of a lot of the work that will be presented here. So for those of you who are fans of breaks, you'll be pleased to know that I decided to structure this into 3 parts. So the first part, which will run till approximately 10 to 3, I'm just going to kind of set the scene. So I'll begin by discussing what I mean by an intractable density and the sort of models and situations they arise in. I'll then go on to discuss what I've here termed pseudo-marginal methods of various types. I'm using that as a kind of all-encompassing term. It might not be the best description, but they do all share some certain properties. So this will include both things that are probably quite familiar to people, like pseudo-marginal Metropolis Hastings, technique called importance sampling squared, which, similar to the pseudo-marginal Metropolis Hastings method, is designed for problems in where we can only estimate a unbiased, we only have access to an unbiased density estimator. And then also this method, variational Bayes for intractable likelihood, which actually David Knott talked about briefly in his introduction to ABC last week. And then to round off this first session, I will try and make some connections between all these methods and discuss how they can be viewed as performing inference on some extended state space, but making some particular assumptions about the kind of approximations that we make on the distributions we're defining on that extended space. So just to also give you a kind of idea of what's coming up in case you want to escape after the break. So in the second part, I will go on to discuss more of the kind of new work I'm discussing here, or at least my own work. So I will define this auxiliary pseudo-marginal MCMC framework. And as part of that, this involves trying to apply different Markov chain transition operators to pseudo-marginal problems. And one of the kind of algorithms we found particularly helpful in quite a wide variety of problems with various slice sampling variants. So I will give a bit of an overview of some of the key slice sampling algorithms. Sorry for those who are familiar with these algorithms, but I just thought it was useful for providing a bit of context to the later discussion of experiments. So let's cover before. Yep. So I'll then talk about the use of slice sampling within a pseudo-marginal context, and this relates to an EI stats paper that myself and Ian Murray published in 2016. And then I will go on to make some links to some very closely related work that was kind of concurrently came out at the same time on arXiv, and that actually Michael Pitt presented on in the opening workshop related method, which is very closely linked to these ideas of auxiliary pseudo-marginal MCMC. And in the final part of the talk, I will kind of change gears a little bit and go on to talk about models in which we're assuming a lot more information is available about the model, in particular that we're able to differentiate through it. So I'll give a little bit of an overview of automatic differentiation. I will define what I mean by this kind of differentiable generative model. I'll talk about this method by Frederick Linston, pseudo-marginal Hamiltonian Monte Carlo, and then also talk about the application of a constrained Hamiltonian Monte Carlo method to performing inference that's in some sense exact as opposed to the sort of standard approximations we make in approximate Bayesian computation in these class of differentiable generative models. So I'm going to be using a lot of factor graphs for my presentation, so I'm just going to quickly outline the notation I use just so that we're all clear when I'm flashing things up on the board later on. So a factor graph just describes factorization structure of some probability distribution. We have factor nodes, which are these little box is on the graph here, and then variable nodes, which are the circles. Latent variables are generally in white. Observed variables will be in gray. If we have a factor which doesn't have any incoming edges, that describes some marginal factor. If we have a factor which has some incoming edges and some outcoming edges, defined in terms of this directivity of this arrow, that defines some conditional factor in our distribution of interest. We sometimes will also have undirected factors, which just specify some term in factorization of the distribution, but without putting any particular semantics on whether this is a conditional probability or not. And then finally, which is just slightly non-standard notation, I will use this little diamond to represent what you could think of as deterministic factors, factors which basically involve some functional mapping between random variables without any additional stochasticity. Okay, so also just a bit of notation. Some of this is more common than others, but yeah, we'll use this color notation to indicate integer ranges. I will use this measure of a function notation a lot where convenient to kind of represent integrals against a measure. Throughout, I will use sans serif symbols to represent random variables, and we'll use this tilde to represent being distributed according to some distribution, and the expectation operator by this bold font E. So the task that we're all in some sense interested in a kind of Bayesian computation workshop is performing inference. And so my summary of what inference is at a kind of high level is that we have some target distribution on some space, and we want to compute expectations with respect to that target distribution. Obviously, in most real problems of interest, we're not going to be able to exactly evaluate those integrals, and so we need to kind of move into the domain of approximate inference methods. So the typical assumption we make in approximate inference is that we have access to some sort of density against a reference measure for the target distribution of interest. So we might not know the normalizer of this density, but if we have access to such a function, we're kind of in the usual domain that we're all quite familiar with and happy with. And then there are a lot of different kind of flavors of approximate inference we can apply. So we can do Monte Carlo methods, be that MCMC or sequential Monte Carlo, or other importing and sampling based methods. We can take variational approximations, be that variational Bayes or things like expectation propagation. But fundamentally, most of these, at least in their standard formulations, require us to be able to evaluate some density function. So what we've heard about a lot over the course of these last few weeks is that there are problems often where we're not actually able to exactly evaluate the density we're interested in. So I'll go on to make this a bit more concrete in particular problems later on, but often if we can't evaluate the density itself, we can, however, evaluate some unbiased estimator of that density using some sort of a Monte Carlo method. Typically important sampling of some variant. So what do I mean by an unbiased estimator? Just to be concrete with notation, I'm going to denote this some sort of function p hat, which takes as inputs both the original unknown z and then some further auxiliary variables u. And then if I integrate out over those auxiliary variables, point-wise evaluated at z, that will give me the density of interest and expectation. So kind of a trivial construction that we can use if we have a particular unbiased density estimator, we can always take multiple such estimators and combine them with just a simple arithmetic mean to get a lower variance estimator. So I'm mainly putting this up here now to kind of define some notation that I'll use later on when discussing these multi-sample estimators. And so in particular, I'll discuss some results that have came out on how we should choose n in different cases. So the first specific case of a kind of model where intractable densities come up that I'm going to discuss is this idea of an undirected model. So this could be sometimes termed a Markov random field or a Boltzmann machine. The key idea is that our probability distribution is defined by some product of unnormalized factors across a set of nodes. And typically, while we'll be able to evaluate the density on here, the x variables up to a normalizing constant, the normalizing constant will depend on the parameters of that model here, which we're denoting z. And so if I want to perform a sort of Bayesian inference in these sort of models, so I want to infer posterior on parameters given observations of these x variables, then I need to be able to evaluate this n of z. So it's a constant with respect to the x variables, but it's not a constant with respect to z. And it involves this integral across the base measure that this density on the x-axis is defined with. So the kind of prototypical example of this in a kind of discrete space setting is the Ising spin model. So here our state space on one of our x's is a binary vector. Particularly in the case of Ising models, we typically consider these binary variables as being distributed across some sort of spatial lattice. And our factors are then defined as kind of these pairwise factors on adjacent nodes within that lattice. I'm going to specifically consider later on this very simplified version of the Ising spin model where we just have two parameters, this interaction parameter j and this magnetic field parameter h. So these don't depend on the indices here, so they're just two scalar constants. So here the state space is finite, but if d is large, this will scale with 2 to the d of the total number of states. So this normalizing constant in this expectation here, or integral here, will involve a summation over 2 to the d states, which, if d is reasonably large, will quickly become intractable, even if we've got, say, a lot of parallel compute. So we're not going to be able to evaluate this density exactly, but are there ways in which we could perhaps estimate this density? So there have been a few different algorithms proposed in this setting. So this class of distributions was termed by Ian Murray in a paper of his, doubly intractable distributions. And one of the first methods for performing inference in these doubly intractable distributions was due to Muller and colleagues. And fundamentally, this method and a lot of the other methods which have been developed depend on being able to generate exact samples from this distribution on the x variables. So this typically is a difficult problem. So for a general Ising model, there aren't efficient ways for generating exact independent samples from the distribution defined by that model. At least not trivial ones. There is, however, this concept of perfect sampling methods, in particular things like coupling from the past, which will allow us, given Markov chains which couple at some point, and then if we kind of consider the infinite history of those Markov chains, we're able to come up with exact samples from this distribution of interest at quite considerable cost. So this is not a cheap method, but we can at least feasibly generate at least a few exact samples from this distribution. So if we have access to exact samples, there's a way to construct an estimator proportional to the reciprocal of this normalizing constant, and that's what we need to be able to come up with an unbiased density estimate. So I'm going to term the U variables here as all of the inputs to, say, the coupling algorithm that we use, or whatever perfect sampling algorithm we use. We'll take a series of random numbers from, say, a pseudo-random number generator. I'm just collecting all of these here into this U vector, which will have some distribution rho, and then the operations which then generate a sample from this distribution phi. Given those random variates, I'm going to term that function S. So this basically takes in inputs as random variables, outputs a sample of interest from this distribution. So if we have access to a function like this, then an estimator which kind of fits the form of the kind of estimators we were looking at earlier is as follows. So we have the original unnormalized density factor here, and the prior on our latent variables, on our parameters. And then we have this ratio here between the value of the unnormalized factor evaluated at some set of reference parameters, divided by the same factor evaluated at the parameters we're currently at. So these reference parameters, any set of reference parameters will define a valid density estimator, but the choice of these parameters is quite key in getting this density estimator to be low variance. So typically in practice, this might be formed by using something like a maximum pseudo likelihood type approach to come up with some set of parameters which are thought to be representative of the system. We could also replace this whole term at the top here with some variational approximation to the density. But the key thing is here we need some integrable factor which depends on the simulated x variables. So if we take expectations of this, what we get in this particular case is that the density estimator is equal to the normalizer of, depending on the z reference terms, multiplied by our target density of interest. So this is just a constant, and so we can just kind of push this through to the constant factors that we can usually ignore in approximate inference. And so this altogether kind of shows that this estimator, if we are able to simulate using these kind of perfect sampling methods, will give us a way of unbiasedly estimating the density of interest. So in practice, if we use a simple estimate like this in a large problem, this can kind of become unusable due to the variance. So there have been kind of extensions to this method. So this method didn't originally have a particularly distinct name, but in Ian Murray's thesis, he terms this auxiliary variable method. In particular, this variant, the single auxiliary variable method. And there are variants using multiple auxiliary variables, which unsurprisingly is termed MAVM, multiple auxiliary variable method, which basically replaces this single ratio with a product of ratios formed using an yield importance sampler type estimator. So we'll come back to this estimator in particular later in some of the experiments. But yeah, this is one particular instance in which we have some intractable density that we can't exactly evaluate, but we are able to, with a bit of work, construct an unbiased density estimator. So the kind of more usual example that we've actually counted many, many times over the workshop so far is latent variable models. So these are usually the kind of prototypical example people think of when they're talking about pseudo-marginal methods. So here we're just saying that our observations depend on some latent variables x, which themselves are modulated by some set of parameters z or unknowns, or which are the actual target variables of interest. And what we'd like to do is evaluate this kind of marginal posterior on our z variables, which is proportional, we can kind of think of as the product of the marginal likelihood and some prior on the z variables. So in general, evaluating this marginal likelihood is going to involve integrating over those latent variables, and that's where we kind of get into the intractability. So unless we're in some sort of kind of conjugate system where those integrals are going to have an analytic solution, we're not going to be able to exactly evaluate this marginal likelihood. So an example of this might be something like Gaussian process classification or regression with a non-Gaussian likelihood. So there we might have some observations which are a set of, say, binary labels, some input features, and now our distribution on the latents, given our parameters, or the kind of hyperparameters here of some covariance kernel, takes the form of a Gaussian process prior. Then our likelihood, say here, is a probit Bernoulli likelihood. And so, yeah, in this case, we're not going to be able to kind of analytically integrate the system. And so if we want to do Bayesian inference, we'll need to appeal to some sort of method which integrates out those latent variables, be that by defining a Markov chain on the whole system or by using something like a pseudo-marginal method. So the more kind of common example, which has come up time and time again within these talks, is state space models. So this isn't the particular kind of factor graph that we've seen many times before, but it's just a kind of collapsed version of it, so we can kind of still think of them within this framework. So I'm not going to really concentrate on state space models here. People have covered them in depth and kind of talked about a lot more of kind of methods of kind of cleverly adapting pseudo-marginal type approaches within the state space modeling setting, which are kind of using the structure in those problems. So I'm largely going to kind of ignore particle MCMC methods and concentrate more on these kind of alternative uses of pseudo-marginal methods. So the kind of general setup, though, for these latent variable models about how we would compute some sort of density estimator would be using kind of some sort of importance sampling-based estimate. So the simplest thing we could do, perhaps, would be to sample from the kind of prior distribution on the latent variables and use that to form a importance sampling estimate of this of the posterior. Typically, in the same way that a bootstrap particle filter will often be inefficient as the dimension grows because it's not leveraging information about observations, this sort of naive importance sampling estimator like that will similarly tend to perform poorly in practice. And so what we might actually want to do is fit some proposal distribution which depends both on the current value of the parameters and the observations, and somehow approximates this posterior on the latent variables x. So if we assume that we've somehow come up with some sort of approximation like this, we can then again form an estimator in this kind of canonical form by kind of factoring out all of the randomness that goes into generating values from that proposal distribution into this S function, and then just saying that our estimator now has this form here, where I've kind of defined this XU as basically the output of that sampling function. So the final example I'm going to talk about, and this one's a little bit tangential, but is something that people who were around last week until David Knott's talk should be familiar with. So a particular class of models which has a lot of kind of applied interest, and as much as it's a very natural way for people to kind of express their prior information about some system of interest, is this kind of class of simulator, or as we had Lawrence describe, programmatic or implicit models. So the idea here is that we don't necessarily have a explicit probability distribution defined over the observation variables and the parameters of interest, but instead we've usually in code defined some function which, given the values of some parameters z, and access to a random number generator, which here I'm just going to kind of concatenate all of the outputs which feed into this simulator into this U vector, will output a simulated observation x. So, yep, as I said, this model is kind of implicitly defined by the program or code which performs that simulation process. We can kind of loosely think of the kind of target density of interest as being this integral against this kind of Dirac delta, or this Dirac measure, between the true observations and the output of the simulator. So in general, this might not even define a kind of density with full support across the real. So this density might not be defined with respect to the Lebesgue measure. If we kind of ignore that class of models, even if we think the density does exist, obviously this integral here is something that's, if this g is a complex nonlinear function defined by some sort of computer program, not going to be something that's kind of simple to evaluate. And so people have tried to come up with various approximations to this density, which we might be able to use more tractably within inference. So the most kind of common class of, at least within a Bayesian setting of inference methods which are used in this case, or approximate Bayesian computation methods, a kind of umbrella term. So the key idea here is that we're going to relax this requirement that the observed data exactly matches to the simulated output, and instead basically describe that there is some probabilistic relationship between that simulated output and our observations. So we can either think of this as some sort of noise process in our model, or just explicitly as some sort of heuristic we're introducing to allow for a finite kind of tolerance between in distance between the real data and simulated data. So then we can define this kind of epsilon ball approximation of our target density just by integrating that kernel, which is kind of our substitution for this Dirac term, against the density, the marginal densities on the random variables and the prior on the parameters. So the nice thing about this form is because this is now non-singular, we can approximate this integral just using a simple Monte Carlo method by sampling u and z variables and then mapping them through the simulator and evaluating the kernel at those values. And so this density estimator is kind of the basis of most ABC methods. And we can use it in various ways. We can use it, say, within an MCMC method. But the actual applications of this tend to boil down the same set of theory which kind of underlies this kind of broader class of pseudo-marginal methods. So that's why I've mentioned them here. And a lot of those same issues which affect pseudo-marginal methods and how efficient they are affect the tractability of applying them in these ABC settings. So kind of an extra note that in practice, actually, we usually can't, even using some epsilon ball, come up with reasonable density estimates using that previous form. So we introduce these kind of extra layer of approximation via a set of summary statistics. So now our kind of approximate posterior or approximate target density will have this form here. So we're kind of mapping both the observed data and our simulated observations through this summary statistic function, giving this kind of approximate posterior here and an unbiased estimate of it here. And so now, unless we have some sort of sufficient statistic, which will generally not be the case, we won't have the case that as epsilon tends to 0, that this density will converge towards the kind of target density of interest. So we're definitely losing some information by doing this, but this is often something that is pragmatically needed to be done in practice to make inference possible. So the kind of the method which kind of underlies the naming of pseudo-marginal in all of these methods that I'm kind of describing here is this kind of pseudo-marginal Metropolis Hastings method, which was originally proposed by Mark Beaumont in this genetics paper, but the actual name and quite a lot of the analysis was performed later in this paper by Andrew and Roberts in 2009. And so this algorithm has this very appealingly simple form, which I think it kind of underlies a lot of why it's so widely used, but it also has some pathologies which make it quite difficult to use in practice, and I'll kind of come on to those later. So the kind of key idea is we're going to define a proposal kernel with a very particular structure such that we get kind of fortuitous cancellations in the acceptance probability, which kind of remove the parts of the problem that we're not able to evaluate. So we define the Markov kernel as being such that we sample the z variables using some perturbative proposal. But additionally, we also resample all the auxiliary variables which go into the density estimator independently from their kind of marginal density row, marginal distribution. So the nice thing about this is if we generate a proposal using the kernel of that form, then this particular acceptance probability corresponds to some particular Metropolis Hastings kernel on this giant space, which exactly leaves the target distribution invariant. And this is behind this name of kind of exact approximation. So here, the actual Metropolis ratio only involves things that we know how to evaluate. So we have this density estimator. Implicitly, this defines the auxiliary variables, but all we need to be able to do is actually evaluate the density estimates themselves. We don't need any particular knowledge of the U variables or their distribution. And then we have some standard proposal density on our Z variables, which typically we will be able to evaluate fairly trivially. So this kind of construction has actually been extended to various different approximate inference methods, and I'm just going to review another two just to kind of highlight the similarities. So this important sampling squared method by Tran et al. Is kind of a very similar construct which takes that idea of using density estimators instead of in place of exact estimates and applies that with an importance sampling setting. So now we define an importance sampling ratio or weight function just as the ratio of our importance proposal distribution Q and our density estimate P hat. So this is a function both of the Z's and the U's, but again, all we need to be able to do is to evaluate the actual density estimates. We don't need any particular knowledge of the U variables. Then if we sample a set of auxiliary variables from their distribution and a set of Z variables from their proposal distribution, then we can simply form a importance sampling, self-normalized importance sampling type estimator for expectations as shown here. And again, similarly to this kind of pseudo-marginal Metropolis Hastings setting, this has a kind of consistency property which comes about from it defining a valid importance sampling estimator on this augmented ZU space. So the final example, which is the one that David Knott talked about, work by him and some colleagues, including, again, Tran. So here, this is the variational approach to inference. So we define some set of variational, we define a parametric family, which we think should be able to approximate the target distribution of interest, parameterized by this theta vector. And we define our variational objective as this KL divergence like integral here. So this looks a little bit mysterious at first, but we'll come on to a later slide to kind of justify why exactly this is a valid thing to do. But if we just assume for now this defines some sort of valid variational objective, then the key thing about this is if we use a kind of score function type gradient estimator form, then we can come up with unbiased estimators of this variational objective just as expectations against this variational approximation, Q, and samples from, again, this row distribution on our auxiliary variables. So in particular, if we kind of take out this bit here, all we're doing then is computing the expectation of this term against those two distributions. And so we have that an unbiased estimator of the gradient is just defined by this G hat function evaluated at independent samples from these distributions. Then we can just use whatever stochastic gradient descent method of choice you wish to try and minimize this objective. And under kind of some suitable conditions on, say, the size of these step size parameters, this should converge to some local minima. So one of the key problems with this method, as with all kind of gradient-based methods using this kind of score function type formulation, is these sort of gradient estimates tend to be very high variance. And so we're either required to use quite a large number of kind of independent samples of this gradient estimator, or a small step size equivalently to get much signal from this gradient. Alternatively, we can kind of try variance reductions methods like control variates to kind of come up with some lower variance estimator. But this adds quite a lot of problem-specific tuning that we need to do. An alternative is to use what's sometimes termed a reparameterization form of an estimator. This involves defining this variational approximation as some reparameterization of a set of auxiliary variables which don't depend on the variational parameters, which we can then map through some deterministic function which produces samples from this distribution. So if we can kind of form it in that way, and that we further can propagate derivatives through this p hat, so that's quite a strong requirement. So if this is some complex estimator, which maybe involves in an ABC setting, some sort of simulator, or it might involve, say, some particle filtering algorithm, it's not clear that we'll always be able to compute derivatives. But if we assume that we can do that and that we can reparameterize our variational distribution, then there are these class of lower variance estimators that we can use. And the kind of use of that within a ABC setting was kind of covered in this NIPS workshop paper called Automatic Variational Inference for ABC, I think, or ABC Variational Inference. So that's very kind of similar in spirit to this variational Bayes of intractable likelihood paper, but just using a slightly lower variance estimator for cases where that is relevant. Okay, so in all of these three cases, we've basically taken some kind of standard approximate inference algorithm, be that a Metropolis Hastings, MCMC method, important sampling, or variational Bayes. And kind of what it looks like what we've done is taken all the terms which involve the density estimate of interest and just replaced them, the exact density of interest, and then replaced them with estimates. And so the nice thing about this particular construction is that it forms very black box methods that need to know very little about the specific form of estimator that we're using. So we generally need access to the computed density estimate, as I've been trying to stress through this description. So we don't need any kind of information about these auxiliary variables or any further information about their distribution other than the kind of ability to sample from it. So this means that we can kind of use these kind of complex estimators without really having, in the inference method, to kind of dig into the details of that and how they use these auxiliary variables within them. So if we just, for kind of convenience in terms of notation, consider that this row distribution has some density R with respect to some reference measure, then we could define an extended joint target density on the Z's and U's as just the product of this p hat, our density estimator, and that R density. And the nice thing about this is, by construction, this kind of unbiased density estimator property means that the marginal under this joint density on the Z's will be the density and therefore distribution of interest. So using that joint density, we can kind of reconsider these existing methods that we've been looking at as what they kind of consist of on this extended state space of the Z and U's with this target density defined by the product of the p hat and R. So our pseudo-marginal Metropolis Hastings algorithm we can think of as we just have the standard Metropolis Hastings form with here our target ratio of target densities, and here the ratio of the proposal densities of the kernels we're using. The importance weights in the importance sampling squared, again, we just have this joint target density on the top, and then a particular proposal distribution on the bottom, which is formed as an independent product of the some proposal in the Z's, and then the marginal distribution density on the U's. And then finally, in the VBIL variational objective, we can see that variational term that we defined earlier exactly corresponds to the KL divergence, or at least up to some normalizing constant between this joint target density on the z's and u's, and some variational approximation, which again assumes that the u's and z's are independent, and that the u's have a density which is fixed and equivalent to the density that they're drawn from in the estimator. So we can kind of see now why all of these methods define these kind of exact approximations. They are just particular choices on this extended state space of, say, an MCMC method, or an importance sampling proposal distribution, or a variational objective, or variational approximation within that objective. So yeah, as we see, once we cancel through these density terms, we get the previous forms for these functions that we covered in the earlier slides. And as we said earlier, the nice thing about these cancellations is that we now don't need to know this density R on the u's, and therefore we don't need to have a kind of explicit access to these u variables. But this assumption of independence between the z's and u's in, say, these proposals or variational approximations could be quite limiting in practice. So this kind of reiterates what I was just saying. So yeah, we're assuming basically that there is no explicit u dependence, or there's no dependence between the z and u variables in our proposal or approximations. But in reality, we know that under this joint target, the z's and u's are dependent on each other. And why is that the case? Well, if they weren't, then we would just have that we were able to exactly evaluate the density, because to have an unbiased density estimate then, we would just need to always kind of output a term depending on P of Z, independent of the U variables. So if the output of the density estimator strongly depends on the U's, that in some sense means that we have a high variance estimator, and we can kind of see there is this duality between the variance of the estimator and the degree of dependence or statistical dependence between those auxiliary variables and the Z's. So rather than the kind of typical idea of trying to come up with a lower variance estimator, we can kind of think of that as equivalently trying to reduce the dependence between the target and auxiliary variables, such that approximations of this of the factored form used in those earlier methods kind of become a closer match to the particular form of the target distribution. So kind of coming back to this kind of earlier idea, of a very trivial way of doing that is taking an average of some simple unbiased estimate and then just coming up with a set of independent such estimators and taking the arithmetic mean across them. So then our joint target density will, on the Z variables and all of the N auxiliary variables, will have this particular form. So if we now marginalize over all of the auxiliary variable replicates except, say, the nth, then that we can show that the resulting joint marginal density on the parameter z and auxiliary variable u has this form here. And so why is this interesting? Well, it kind of provides an intuition behind this idea that this is a lower variance estimator and the link to the kind of decreasing dependence between the variables. So as n becomes large, only this term will tend to dominate in this density, so this term will become increasingly less significant. And under this term, the z's and u's are independent, so there is no interaction between them. It's only through this estimator that there is dependence between the current z values and the u's. And so increasingly, as we increase the number of important samples, this kind of assumption of independence between the auxiliaries and target variables will become valid, but obviously at some potentially very high cost at evaluating all of these independent density estimators. So this kind of idea was considered somewhat more formally, and specifically in this particular paper within an ABC setting, in this recent paper of Luc Bohn and colleagues. This comes up with this kind of guideline for choosing the number of important samples within the density estimator used in an ABC setting within a pseudo-marginal MCMC type approach, and gives this guideline that under an assumption that the cost of evaluating each density estimate is constant, such that the overall cost of evaluating n density estimates scales linearly with n. So what this is kind of ignoring is if there is, for example, some fixed overhead or values that can be pre-computed in this density estimate, say, which can then be amortized across different individual instantiations, or maybe if we have access to parallel compute resource such that there isn't this kind of linear scaling with the number of samples. But under kind of the more simplifying assumptions that those cases don't apply, we can they show that using one important sample is close to optimal in terms of the asymptotic variance per density of evaluation. So close here is, I think, within some factor of 2. So this was for a specific case of an ABC type estimator where we're using this very particular uniform Ball kernel. So this result was extended by Chris Sherlock, Alex Thierry, and I get the last author in this 2017 paper to the more general case of an average of n arbitrary density estimators. So to kind of come up with some measure of computational cost, you again have to make this assumption of a linear scaling of cost with n. But under these more general conditions, again showed that using one important sample is in some sense close to optimal. And so in this simple important sampling type setting, there is no real need to kind of tune this n variable in a pseudo-marginal setting. And for people from a particle MCMC type context, this might seem at first counterintuitive because in that setting it is very much the case that the number of particles we use in our particle filtering based estimate of marginal likelihood is key to determining the success of particle MCMC methods. But the kind of estimators we use in that case don't have this simple form of an average of unbiased estimators, and so all of the results in these papers don't apply. So that's why all of the kind of previous work showing about how we should adjust pseudo-marginal methods density estimators to kind of control the variance of those estimators by adjusting these number of samples, while relevant to the kind of particle filter setting, they're not so interesting in the kind of simpler case of these important sampling trait estimators, and we can kind of generally get away with, at least asymptotically, using just one important sample. So yeah. So just to kind of conclude this initial section, so these are kind of questions I'll hope to try and follow up in the next part of the talk. So we've considered the specific form of Markov transition operator defined on this augmented space, defined by the pseudo-marginal Metropolis Hastings algorithms, which, as we said, have this nice property of being quite black box, so we didn't need any explicit knowledge of these U variables or their distribution. But as we'll see in practice, it often tends to perform quite poorly. So as these kind of pathologic sticking behaviors where it will have a very long series of rejections. This both makes it quite difficult to tune this algorithm because we're getting a very noisy signal, say, from the exceptions probabilities, but also obviously limits the overall kind of asymptotic efficiency of that, of chains using that approach. Then the follow-up to that will be if we kind of give up being able to be completely agnostic to the kind of form of distribution on these auxiliary variables. So we assume that we maybe have some more knowledge about them, be that being able to evaluate the some density on the distribution of those auxiliary variables, or even compute derivatives with respect to those auxiliary variables. I'll also kind of consider whether or not we can use this additional information to kind of further define more efficient MCMC methods, which might be more scalable to these kind of high-dimensional settings that we're maybe interested in. Okay, so yeah, this will hopefully be covered somewhat in the next two sections. Okay, so that's the end of the initial part.